right? But so far what we've got then is this identity that the complex log of 1 plus it can be expressed as the ln of the square root of 1 plus t squared. Oh, and by the way, notice that that is nothing but the modulus of this complex number. So I'm going to write it that way. Right, see, the modulus of a complex number is just given by the square root of the sum of the squares of its real and imaginary parts. Real part happens to be 1, and then the imaginary part is t. So you take the sum of the squares of those, and then you have to take the square root of that. All right, so anyway, it's like the modulus of 1 plus it, okay, plus I times capital A of t. And this is where t has a modulus strictly less than 1. Okay, so the next thing I'm going to do is I'm going to show that this logarithm is indeed cancelled out by an exponential. Okay, so I want to prove that if I take e to the power log of 1 plus z, I do indeed get 1 plus z. And this is provided z is of modulus less than 1, simply because that's the only case I defined this logarithm thing. The complex logarithm. I only defined it for numbers of this form, 1 plus z, where z is of absolute value less than 1. I haven't defined it in any other case. So that's why the same restriction has to apply here. But I want to prove this cancellation law. Right, now, before we can do that, though, we have to understand that, you see, log of 1 plus z is a complex number. It's going to have some real part and then some imaginary part. And so to even say what e to that thing means, we have to say what e to the a plus bi means. That's the question. What does, we have to give a definition to e to the a plus bi power in general. Right? But fortunately, that's very, very easy. Here's the idea. We're just going to define e to the a plus bi, where a and b are real, I should say. So e to the a plus bi power is going to be defined as e to the a power times e to the bi power. Okay, that's the most natural definition you could possibly make. Because we know that in general, like e to the x plus y is supposed to always come out to this. Now we proved that for 2 reals. And then separately we also proved it for 2 pure imaginaries. Right, so both of these were things like this one we proved in class quite a while ago. And this one we proved recently in one of these videos, like in this series of videos. So this represents the case where both terms are real. This represents the case where both terms are pure imaginary. And now we have a case where one term is real and the other one is pure imaginary. So since it's the same pattern in the other 2 cases, where e to that power breaks up as a product, right, it makes sense to just define this expression as the product of these 2, to be consistent with those other 2 cases. So we're just going to take that as the definition. Okay, and then you can check that the laws of exponents hold as a little theorem, just to check the consistency of all this. We want to check that the laws of exponents hold. So for example, let's say I do e to the z times e to the w. The question is, will I get e to the z plus w? Well, yes, because if z is a plus bi, and w is c plus di, where a, b, c, d are all real, this one is going to be that. This one is going to be this. And by definition, this first thing looks like that. And by the same definition, the second one looks like that. Right? But then you see that this is just a product of 4 complex numbers. Actually, these are even real. If a is real, then so is e to the a. In fact, it's not only real, it's positive. So, these 2 happen to be real, but reals are also complex. And so we have a product of 4 complex numbers. We can reorganize it like that. And then using the exponential law for real exponents, we get that. And using the exponential law for pure imaginary exponents, we get this. Okay, and then that's the same as this. Okay, just basically by this definition again. It's like this same definition, just read in reverse. If you ever have e to a real times e to a pure imaginary, you go this way in the definition, and it just allows you to combine the 2 exponents. Okay, so that's what I did here. I had e to a real number times e to a pure imaginary number, and I could combine those 2 as a single exponential just by the definition. This is simply the definition of that expression. Okay, but then you see what that is. That's just exactly z plus w, because that's the way you add complex numbers. You just add their real parts, and then you add their imaginary parts. So that's exactly the exponent here we have up there. Okay, so indeed, if I start with e to the z times e to the w, I do indeed get at the end e to the z plus w. Okay, so the laws of exponents keep holding true. So that tells us that this is a good definition. This definition has the intended properties. Okay, and now it at least makes sense to raise e to this complex power, because we now have a definition for e to any complex number. All right, so, but specifically, how do we know that e to the log z, or 1 plus z, is just exactly 1 plus z? Okay, well, it's easy. I'll show you how it works. First, I'm going to state a lemma, which is very similar to a lemma that we proved in class. It's just like the complex version of it. And what it says is that if I have a complex sequence that's converging to a limit, then we can form this expression, and that will also converge to a limit, namely e to the w. Okay, where, again, e to a complex number was just defined in the preceding couple of slides. This definition here. I should emphasize, like, for instance, how would I do e to the power 2 plus 3i? Well, by the definition, it's e squared times e to the 3i. And then e to the 3i, by Euler's formula, is cos 3 plus I sine 3. So then you can just distribute the e squared, and so you see that the real part of the answer is e squared cos 3, and the imaginary part of the answer is e squared sine 3. Okay, and you can calculate e squared by this series. At least, you can, by summing lots of terms of that series, you can get a close approximation. Okay, and then cosine 3 can be computed from this series. And so on. So then, by multiplying those values, you get the real part. Okay, so yeah, we now know how to raise e to any complex number. So e to the w makes perfect sense. And that's going to be the limit of this expression here. Okay, so we proved a lemma very similar to this in class already. It just went like this. Like if I had some sequence yn converging to y in the reals, then 1 plus yn over n to the power n converges to e to the y. That's like the real version of it. And it's the same. Like the proof is virtually identical. Actually, not virtually, it's literally identical. Because the proof just involved like estimating differences, estimating the absolute value of a difference using the triangle inequality. So just to give some reminder how it works, we can use our basic expansion. Right, we had that basic expansion, and then we, whoops, sorry. What do I want to say here? Yeah, so actually, as a first case, we can imagine that w is 0. In other words, the limit, right, the limit of the w sub n's is 0. Okay, and in that case, it's pretty easy to see what happens. We can subtract 1. And the 1 is conveniently here, so we just move it over. Then you just take absolute values, and you'll be left with the absolute value of this entire sum. So by the triangle inequality, that's like less than or equal to sum of the absolute values of the terms. Okay, now all these factors here are positive and less than 1. So we can upper bound them by 1, and we're just left with then this as an upper bound. And even better, even simpler is this. Okay, because dividing by j factorial makes something smaller. Right? Now, as long as the modulus of wn is less than 1, then we can also say that this is less than or equal to the full geometric series, where you sum all the way to infinity. Because the common ratio will be, like, right, in the correct range. And so this geometric series will converge. And what it converges to is exactly like the first term of the series divided by 1 minus the common ratio. Right? The first term of the series is just this because j begins at 1. So right, this first exponent is a 1, so the first term is that. Okay. Anyway, this does eventually happen. This is eventually true for all sufficiently large n, because wn is on its way to 0. So as n increases, like, there will come a point where, from that point on, the absolute value of wn is less than 1, right? Because, you know, on its way to 0. Actually, these are complex numbers, but still. The wn's are on their way to 0. So eventually they have to get within 1 unit of 0. And they have to stay within 1 unit of 0. So yes, this does happen, at least for all sufficiently large n. And it's only for large n that we care about. Because remember, the whole point in this theorem is to evaluate the limit as n goes to infinity. So it's only large n that we care about anyway. So the fact that there's this cutoff really doesn't bother us at all. We just consider only values of n beyond that cutoff. And then let n continue to get big, to continue to, like, go to infinity. Okay. Anyway, so we get this upper bound. And it's very clear that this upper bound goes to 0. Because you see that the wn's are going to 0, which means the top is going to 0, right, by this assumption. But then the bottom is going to, like, 1 minus 0, which is 1. So the whole fraction is going to 0 over 1. Right, but then you see by the squeeze theorem, since clearly any modulus is greater than or equal to 0. And then we have an upper bound that's also going to 0. So the squeeze theorem tells us that this thing in the middle also has to go to 0. And that means that 1 is the limit of this expression here. Okay? So what we conclude is that if Wn is approaching 0, then 1 plus Wn over n to the n is approaching 1. Okay, then the general case works like this. If Wn is approaching W, then we can write Wn as W plus a difference, where the difference is going to 0. So in other words, the dn is defined as Wn minus W. And that's going to 0 because that's equivalent to just saying that Wn is approaching W. These are equivalent formulations. Okay, and then if we look at this expression here, so we can basically factor it. Okay, something like that. We've seen this argument before. If you take this factor in, like multiply it by the 1, first of all, you have to combine the two nth powers. But if you take this factor and multiply it by that 1, it's going to give you the first two terms. So actually, I should just have a dn there. Right, and then if you take it, take the same thing and like multiply it by this second term, the denominator will just cancel with that whole thing, leaving you just that, which will give you this last term here. So it's correct factorization. Okay, but then we can simplify a little bit. So let's see what we have. We have dn, and then there's like 1 over n, which can go in the bottom. Yeah, so that's equivalent. All I did here was I just traded the denominator of n with this denominator here. Actually, I got that a little wrong, didn't I? Sorry. So I just basically traded the two denominators. Swap them. And that's obviously algebraically, right? So like if I have, x over y and then I divide it by z, that's the same as just x divided by y times z. And since these two factors can be swapped in that product, I can also think of it as just swapping these two. That's kind of what I did here. All right, well, that's good because this factor clearly approaches e to the w. And then this factor approaches 1 by case 1 that we've already completed. And that's simply because, you see, this number in the numerator approaches 0. Because dn approaches 0, right, as we said here. And then the denominator is just approaching 1 as n goes to infinity. So the fraction dn over 1 plus w over n is approaching 0 over 1, or in other words, 0. Okay, so yeah, anytime you take something that goes to 0 and you divide it by n and then add 1. So yeah, take something that goes to 0, divide it by n, add a 1, and then raise to the nth power. That factor must go to 1. That's exactly what we just proved, right, in the first case of this proof. So then the limit of the entire expression is e to the w times 1, in other words, e to the w. And that's exactly what we wanted. Okay, good. So how's that relevant to us? All right, well, let's remember this particular sequence wn that we started with when we defined the log, complex log. Here we're back to the situation where z is of modulus less than 1. And remember that we proved that wn approaches a limit, w, which we called the complex log of 1 plus z. It's just some particular complex number. We know it as a series. Right? We know this as a series. The series looks like this. Okay, anyway, so follows that 1 plus wn over n to the nth power must approach e to the w. In other words, e to the log of 1 plus z as n goes to infinity. But we can actually work this out explicitly. If you just look at the formula for wn, look what happens. You just divide it by n. That will take this factor of n right here and put it on the other side as a denominator. Right? Then we can grab this minus 1 and move it over to the other side. Right? And then we can raise both sides to the power n. And so what we get is this equals simply 1 plus z. So this expression just equals 1 plus z for all n. And so in other words, it's a constant. And a constant also approaches itself. So on the other hand, this thing is also approaching 1 plus z, because in fact it's equal to 1 plus z. But now you see that there are two limits for the expression. And the same one complex sequence cannot have two distinct limits. A complex sequence either doesn't have a limit at all, or it has a unique limit. So that means that the two expressions for the limit must be equal. And that proves the theorem that we wanted, which is that e to the power log 1 plus e is just 1 plus e again. Okay. All right, so good. Now, here's where we are. If I look at this particular situation where z is pure imaginary, the same theorem we just got applies to that case, of course, as long as t has absolute value less than 1. Okay, but we also know an expression for this. Its real part is ln of ln of the modulus, and its imaginary part is this new function we called capital A of t, which is defined by power series, like that, provided absolute value of t is less than 1. Okay, so what I'm going to do is just substitute this expression, and by the way, notice that this is real. It's the natural log of a positive number. How do I know that that's a positive number? Remember, natural log only makes sense for a positive number. So how do I know that this modulus is strictly positive? Couldn't a modulus be 0? Okay, yes, a modulus in general can be 0, but not this, because this is 1 plus t squared is definitely at least 1. And that's because t squared is non-negative. T is real. So you see that this modulus here is at least 1, so certainly positive, strictly positive. And that means its natural log makes sense, and its natural log is certainly a real number. And then also a of t is a real number. Because, you know, if you just look at the series, t is real, and so are all the powers of t. So all the terms of that series are real, and of course, a series with real terms would, you know, if it converges to a real sum. Okay, no, so the reason I'm emphasizing that is just because I want to make it clear that when we write this breakdown here of this log, it's like this is the real part of that complex number, and this is the imaginary part of that same complex number. Okay, so then I can just take this breakdown into real and imaginary parts and substitute that into this exponent. So instead of writing that exponent in this form, I'm going to write it in the form ln of the modulus plus I times a of t. Okay, and then notice that that's just of the form e to a real plus pure imaginary. And we just got through defining what that means, right? We said e to the a plus bi, where a and b are arbitrary real numbers, was by definition e to the a, e to the bi. So using that definition here, we get e to the ln of this modulus times e to the I a of t. Okay, and then notice that e to the ln of anything, those two cancel by a cancellation law for the natural logarithm that we developed. Right? We fully proved that in class. So I can cancel e and ln there and just leave the modulus of that number, and then e to the I times a of t. Okay, but on the other hand, we've already proven that this is nothing but 1 plus it, because, you know, in general, when we have this cancellation rule, where was it? Yeah. So like the complex exponential and the complex logarithm cancel when they're in direct contact. So that's what I have exactly going on here. I have a complex exponential with a complex logarithm kind of in direct contact with it, and they just cancel each other out, leaving this number inside. Okay, so now I have this very nice identity, which is that, okay, provided t is of absolute value less than 1, 1 plus I times t is its own modulus times e to the I capital A of t, where capital A is that function that we defined, right, by series. Okay, so what we've got so far fully solves the angle measure problem for points on the unit circle between this line and this line, at least on the right-hand side of the y-axis. In other words, if I look in this quadrant, strictly between those two lines, we can describe that region by saying that x is positive and that y is strictly between negative x and x. Right, so like you just pick a positive x value, here, just choose any positive x value, and then you have to go along that vertical line from like y equals minus x to y equals plus x. So y stretches between those two limits. Okay, another way to say that is that if I divide y by x, then that's going to be between negative 1 and 1. Okay, because x is positive, I can divide through all three of these by x without changing the inequalities. And then yet another way to say it is that the absolute value of y over x is less than 1. So that's the region. Okay, so within that region, we have a solution now because, not including these endpoints yet, the points on these two rays. So I'm going to delete those points. But I'm just talking about this like open-ended arc of the unit circle. For any point on that, we can define rigorously its principal argument now. So let me show you what I mean. I take some point on there. Let me call it z. So z is x plus iy. And since its modulus is 1, remember that the modulus is just radical x squared plus y squared. So that just tells me that x squared plus y squared is 1. I mean, that's clear, right? Because z is nothing but the point x comma y. So if that point is going to be on the unit circle, it has to satisfy the equation of the unit circle. Okay, but also I'm assuming that z is in this region, this red shaded region. So in other words, I'm assuming that x is positive and that the absolute value of y over x is less than 1. Satisfies this inequality, in other words. So here's what I can do. I can look at z and I can think of it as 1 plus I times y over x divided by the modulus of that. All right, so the first thing we should do is just check the validity of that expression. So let's just quickly do that here. Okay, so what I'm going to do is just take this expression and multiply top and bottom by x. Okay, and let's recall x is positive by assumption. Okay, and so we can take that factor of x and like distribute that. And then the other thing is on the bottom we can just write x as its own absolute value because x is positive. And then we can combine the two absolute values and of course distribute the factor of x inside. So that's going to give us x plus iy, right? Because when the x comes in and just hits this term, it's going to cancel the denominator of x, just leaving the y. So yeah, that'll be on top. And on the bottom you'll have the exact same expression, but inside the modulus sign. Okay. But then don't forget the modulus is this. And we know that that's equal to 1 because of the way we chose the point z. So indeed, it's a correct expression for z. Right, but notice that that's in the form 1 plus it over the modulus of 1 plus it, okay, where t is y over x. And notice that that has absolute value less than 1. We have to check that. And it is indeed the case, because that's exactly what this says. After all, t is just a shorthand for the number inside the absolute value sign. So yes. So that's why it's this region. The need to have t have absolute value less than 1 is why we had to restrict to this red shaded region in the first place. Okay. All right, so anyway, we have now written z in that form. And let's remember we have this identity, 1 plus it over its own modulus, can be written as e to the I a of t. So we have z equal to this, okay, where t is just a shorthand for y over x. So you see, we've now determined a theta naught. Remember, the problem was to find some value theta naught, which is real, such that z can be expressed in the form e to the I theta naught. Well, the solution, as long as z is in the shaded region, let me give that shaded region a name. I don't know what to call it. I'll call that shaded region like script r. Okay, it's defined by these inequalities. So basically, I'm formally defining some subset of the plane, script r, as the set of all complex numbers x plus iy, where x is positive and y is strictly between minus x and x. So it's the red shaded region. But notice that it doesn't include the these two rays here. It doesn't include those two rays. It's just everything between the two rays. In other words, it's like the interior of an angle. Okay, why not? Well, because on those rays, y equals x, or y equals minus x. And so you would have this equality. You wouldn't have this inequality. Or you would have the other equation rather than this. So those two rays themselves don't actually count as being in that region. Okay, but as long as z is in that region, and of modulus 1, so that it's on the unit circle, then the solution is we can take theta naught to be a of y over x. Capital A of y over x, where, you know, y just means the imaginary part of z. Well, okay, let me write it this way. And then x is the real part of z. Because remember that z was just x plus iy, where x and y were real. So x can be represented as the real part of z, right? And y can be represented as the imaginary part of z. All right, so y over x is the ratio imaginary part of z divided by real part of z. And then if you just plug that into the capital A function, that gives you a theta naught. So in other words, the principal argument of z can be defined, at least for z in that region, and of modulus 1, we can define the principal argument of z as capital A of this value. In other words, that fraction, let's see, it's like, remember, it's t minus t cubed over 3 plus t to the 5th over 5. So the next term would have 1/3, and then that same fraction cubed, and then a plus 1/5, and that same fraction to the 5th, and so on in that pattern. Okay, and we know that that's a convergent series. And the reason it's convergent is because the ratio in question, if we take its absolute value, that's like what we call t, that's less than 1 by the fact that z is in R. That's why we needed to restrict z to be in that particular region, okay, to get the series to converge. But anyway, we now have, you know, a good expression for the argument of z, and remember that or principal argument, and then also remember that we extended the definition of principal argument so that if I rescale that point z by any positive scalar, we just define that to have the same exact principal argument as z itself for all r greater than 0, strictly greater.